All right, terrific. Good morning. Any questions from last time? Any questions right up front? No? Okay, we'll just get straight into it then. Today, we're going to cover the big three items in computed tomography, and that is the radon transform, the projection slice theorem, and convolution back projection. This is the foundation of CT, radon transform being the math, and then the projection slice theorem being a realization of what these projections mean, and then how do you make a picture using your raw data, and we'll see that that's called convolution back projection. And just to restate the problem, we have parallel beams of X-rays going through the patient here, as shown here. Along each beam, we get attenuation of X-rays such that there's a modification of the X-ray intensity as that beam comes out or exits the patient. And we create a function which we've called G, little g, at each detector position, or a coordinate L along there. And its height is proportional to how much X-ray attenuation occurred. So if there's a lot of attenuation, G is high. If there's not much attenuation, G is low, okay? By its definition. Okay? And our goal is to reconstruct an image of the linear attenuation coefficient values inside the patient for that slice. So as a function of X, Y in the plane of our image, we're going to get a linear attenuation coefficient value at each point. That's the picture that we're going to make. We don't have that. What we do have are these 1D functions G, L, theta. So for each projection angle, we have this G as a function of position along our detector. And so this inversion problem is what we're going to attempt to accomplish. We talked about the difference between having a parallel set of X-rays for one acquisition on my detector versus what actually happens, which is a point source of X-rays which fan out over an angle of about 45 to 50 degrees. And so during the collection of data on our sampling grid, we have many different thetas being sampled simultaneously. And then as we rotate the source and the sampling grid, we will bin all of those thetas and put them back together. Right? So we will eventually be able to re-bin all of these rays such that for a specific angle, we can get a set of parallel rays through the sample. Right? It tells you that the parallel ray here was actually obtained at a different time than the parallel ray here, right? Slightly later or earlier time. But that difference in time across the sample is however much the gantry rotates, over one detector length. So it's not that much. It's like 50 milliseconds or something. When we create the picture, we'll just look at what the pictures look like first. We're going to reconstruct the linear attenuation coefficient value. And early on when this was first created as a medical imaging device, it was thought, well, these are floating point numbers, they're real numbers, mu values. We need to scale it to some kind of integer value that we can display on our very elementary digital display unit. And so what was done is the mu values were scaled with respect to the mu value of water. And so for our system, we will image what the value is we get for water. We will image what the value is we get from air. So air is essentially no attenuation. Water is the attenuation of water, right? And we'll use those two values to scale all the rest of our values. And these are called Hounsfield units after Gregory Helms, Jeffrey Gregory Hounsfield. Air is set by definition to -1,000. So when I measure my value on my scanner and I put nothing in the scanner, I just image air, I set that to -1,000. That's done every day at least on a scanner. It's a calibration. And then we put a water phantom in every day and find out what that value is. And then all the CT numbers for that day are scaled accordingly. So water will have a CT number of 0, right? Air has a CT number of -1,000. And anything like bone or muscle that attenuates more than water will have a CT number that's higher than 0, right? So it's the fractional difference between water and whatever the substance is times 1,000. And this gives you some very nice integer values over between -1,000 to about 5,000. And back in the day when digital encoding relied on smaller numbers of bits, you know, you needed something that was in that order. So what do the CT numbers look like in an actual image? Here's an image of a patient's chest. This is the blood pool of the heart with contrast in the blood, so it's attenuating more X-rays. It looks brighter. Hounsfield units will be larger. This is myocardium, just like muscle. Chest wall, this is actually fat. This is the skin here, and this is subcutaneous fat, some muscle in the chest, bone, the aorta. So if we look at what the Hounsfield units are for these various tissues, skeletal muscle is about 100, fat is -120, somewhere in that range, so it's negative. It attenuates less than muscle or water. Bone attenuates far more X-rays than does water, and so it's 750. Blood with the contrast agent is similar to that bone, which is 650. Myocardium is like skeletal muscle, basically 120. And then here's a little piece of calcium in this patient's aorta, and that's up at 1,300. So it's very high. It's attenuating a lot of X-rays. It's going to be a very bright signal. This thing here is an ECG lead. So it's a metallic cable lying on the patient's chest. And most metals attenuate X-rays very well, one, because they're very dense. Okay, the metal is a very dense material. And so the Hounsfield unit there is 5,000. If we look down in the background, forgetting about these things up around 0, 100, 5,000, look down here in the lungs and in the background air of the image. Air, when you measure what that value is, it's -1,000 by definition on your scanner. And the lung tissue here is about -800. So it's very similar to air, but there's some other stuff in there that's attenuating X-rays. And so those, if you want to look at the lung parenchyma or the lung tissue, you need to adjust your center and window such that you push down into the details down at these Hounsfield unit values, right? As opposed to up here at 100. So let's, we know how we've obtained the data. We'll look really quickly at sort of a first principles way that you could reconstruct an image. Yes? Oh, the quality assurance phantom. I can actually, if you remind me, send me an email. I'll bring a picture of one in next time so we can just look at it. But that phantom is, every day they put this phantom in the scanner and it has water in it. It also has some features that you can measure spatial edge, fidelity and parallel lines, how well they're imaged and stuff like that. And so essentially you image that every day just to make sure the scanner is producing the same picture every day, right? Fundamentally, what it is required for each day is to measure what water is producing in terms of X-ray attenuation. Why would it be different from day to day? It's a good question. You should be asking yourself, why do you have to just buy the scanner and you should do the same thing every day? Not necessarily. If the voltage lags a little bit on the X-ray tube, right? Just like your oven, like when you set your oven to 450 at home, but all of our ovens, if we put in a thermometer, it's not going to be exactly 450. It's going to be this and that, right? And it depends on a lot of things. So the X-ray tube can sag a little bit. The X-ray energy coming out of the tube can be modified a little bit, et cetera, et cetera. And so these things are tuned up, but it is getting reproducible data. It is imperative that you calibrate the scanner every day. And so that's what the quality assurance phantom is there for. And it, you know, when you come in to any X-ray suite, you will see that's the first image that occurred that day. It occurred at 6 in the morning when the tech got there. They just put the phantom in, scan it. It's all done automatically. So let's look at a really trivial image. This image is a 2x2 pixel array, right? And we're going to try and figure out what the values are of the linear attenuation coefficient in these 4 individual boxes. So this is our first image, is a 2x2, very, very low resolution, right? Well, not necessarily. If these boxes were 2 microns, it would be high resolution, but it's a very small field of view. So we're going to produce numbers, relative amounts of X-ray attenuation, this little g function. When we shine X-rays this way, right, we'll get attenuation by this box, and that will give us a value here of P1. We're calling this P for projection. Shine X-rays through here, we get a different value for P2. These are the things we measure. We don't know these things. Then we shine X-rays through here, get P3, shine X-rays through here, get P4, right? So now, given those 2 projections, we've only taken 2 projections for this object, but we have, you know, 4 values we've measured, right? And we've got 4 unknowns in here. So just from the principle of linear algebra, right? If you have 4 equations, right, and I've got 4 unknowns that I'm solving for, I can just write this in matrix form, right, and solve for these values. I know these values. This is just my experiment as to who's being added to whom for each projection, right? And so I can solve for these just by inverting this matrix, right? It turns out this one projection this way, one projection this way isn't enough, because this matrix is actually not what's called full rank. It means one of these equations here can be derived from the other 3, any one of them, right? So you actually need a different ray, one that's coming in at an angle this way, in order to get a full rank matrix and solve this problem. And so we do that, we get a P5 over here. And with that matrix, we can now solve for all of these. However, as this problem gets bigger, this matrix gets enormous, right? So this matrix is proportional to n squared, where n is the number, the dimension on a side, okay? And so basically for an n by n image, we have n squared equations, and it requires the inversion of an n squared by n squared matrix. So 512 by 512 would be a 260,000 by 260,000 matrix that you'd have to invert. You can do it, but it's not terribly stable, right? There are a lot of solution, you know, minima, local minima, et cetera. It's a hard thing to do. So people don't do that for these high resolution imaging applications. There's a simple sort of gestalt way of using your projections to create an estimate of the object that's in there is called back projection. And in back projection, what we're going to do is we'll take the values that we measure from our parallel beams, okay? So this is our underlying, now we're growing in image size, we're at 3 by 3. And this is a 3 in here, and everything else is a 0. Let's see if we can reconstruct this picture. So we have these values, I have a diagonal value here and a diagonal value here, okay? And so when I cut across here, I get 0 attenuation. When I cut across here, I get attenuation of 3, right? And here I cut across here, I get 0 attenuation. So these are my values. So one way of doing this, when we have this projection and we get a value of 3, we don't know where this value of 3 came from. It could be 1 plus 1 plus 1. It could be 3 in this box. It could be 3 in this box, 3 in this box, 2 in this box, 1 in this box, etc. Right? We don't know where it came from in that horizontal direction. All we know is the sum of those mu values across the object comes to 3. Right? So when we make our first estimate, we're going to back project all of these values across the field of view. When we do that, the 0 back projects to every box is 0. And the 3 back projects to every box is 1. We're just going to divide that 3 by the number of pixels across that direction and just put that in every one. That's a fairly, reasonable guess because we don't know. We've just distributed it across the entire space. And we'll back project this 0 across as 0. Right? Now we're going to back project this value. Okay. When we look at, so this projection across here, we have 3 that's going to be projected across all the diagonal ones. And remember, we have a 1 here already. So when we do that projection, we get a 1 plus 1, which is 2, and a 1. Right? So it's just added on top of what we already had. Right? And then out here, because we already had this 1, it's still there. Right? These are still there. So we got a hump in the middle, starting to get a little bump in the middle. Now let's project down this way. I don't change anything in this column because this is 0. I have to distribute this 3 across this entire column. So I put a 1, I add 1 to this, it makes it 3. I put a 1 here, add 1 to there. And then here I don't change anything because there's a 0. And now we look at this projection and do the same thing. And we get a final picture that looks like this, which is not a bad picture estimating this object, right? It's got a bump in the middle. It's pretty well uniform on the outside. And so this is called back projection. Yeah.
I noticed that now it adds to like 5 and 3 instead of 3 and 0. Enough like the sum of the sections.
Yes, they are. So it's basically this is an excellent point. Here's our first estimate of the picture. And now what could you do? You could take your estimate and project it and see, does that match my data? Right? So what you're describing, what you said is the insight is to, hey, why don't we do iterations? And we'll do an iterative reconstruction where I project my guess, my image guess, and ask, does it match my data? When it doesn't, you make some correction and do it all again, right? And you just keep iterating until you get as close as you can to your raw data, right? And so that's called iterative reconstruction. It's actually time-consuming and computationally time-consuming, but you can get very close to the real answer by doing that. That's a really good point. This is like naive back projection. Okay. So let's look at how this works for, say, a simple object like a disk in the plane. If I had a disk in the plane at this position and I look at my projections, here's just 3 projections. For each projection, I'll see this hump, which is the vertical integration through a circle, right? And so that's what each one of these points is, the integral through a circle as we go from the top to the bottom at some displacement from the center, right? I change the angle, I get exactly the same function because the circle is symmetric with theta, right? But it just it shifts its position along this direction. And remember, this is the L direction in our projection space. And then here's another one, it shifts. So if I just back project this one, and I back project this here, and I back project this one down there, I get a pretty good estimate of where that single circle is, right? This is our picture. This is obviously not the object. It's wrong, right? The object doesn't have these rays coming off of it, right? So it's an incorrect picture. However, it does have a maximum, at least at the place where our circle is, things like that. If you do more and more angles, you will generate a picture that looks something like this, where you get a peak, a soft kind of, hump peak that looks much like this, right? At the location of the center of that circle. So it's a reasonable, approximation to the object. This is, again, naive back projections. That's, yes.
So what happens is that it's going to be detected?
Yes, we would. And we're going to see that we don't eventually, in about 10 slides or so, we'll see we don't do this, right? And the reason we don't do this is it gives you a poor estimate of the image, actually. And it's a reasonable approach, right? But as you can see, if I plotted a profile through this object, it would not look like a profile through a disk, right? It would be some kind of, smoothed out blob. And it has a very poor spatial resolution and a bad point spread function. Everything gets blurred out, right? Doing this, right? And we're going to see through a little bit of algebra what you can do to your projections to fix this problem, this blurring problem. There's a MATLAB function that I've put up in week 3 or in the modules that you can play around with what is called the radon transform and look at different projections and using different numbers of projections, etc. We will probably demo that towards the end of the lecture. Okay. Okay, so that's the end of that one. So this is, make sure I got the right lecture up here. 6, good. Let's start here. Okay. This is what this is from true data of a patient's head. And if I have one GL as a function of theta, so one theta value, one projection, and I project it back over the field of view, this is what it looks like. So that's one projection. The interesting thing here is we're going to see how the object evolves or develops as we add in more projections. Okay, and this is not done using just back projection. This is done using the actual method of projection we're going to see, but it's a very interesting demo. You can see how the object kind of emerges as you add more projections into it, right? If we go back here, here's one projection, a group of projections that are close together in theta, adding more projections. You can see we've kind of reconstructed a lot of good edges in this direction, like perpendicular to this line. We have all of these edges nicely reconstructed, but edges in this direction we have no idea about because all of our projections thus far have come from this direction, right? So as we add in those projections, we will see more edges in that object. So it comes around, we build those edges, we've gone through 180, and then we get right to the end, right? And then that's the object. After you have done approximately 400 projections or something and put it back together, you get this. Okay. Let's look at how we can look at our data, which is the projections themselves, as a function of theta, as a function of angle. Let's look at this object. This is very much like a standard quality assurance phantom, right? It has a uniform background. It has some air holes here So there should be very little attenuation here, and it has ellipses which are emulating bone, right? So high attenuation. This is the actual patient table. That's what we're seeing down here. And so here's a single CT image of an axial section to that phantom. This is what is called a sinogram. And a sinogram is all of those GL thetas stacked one on top of the other as a function of theta. Okay. So this direction is L. Do I have the coordinates here? Okay. This direction is L. This direction is theta. So I take say 400 different theta values, and for each one, I look at my sample, right, and I plot that and then stack them all one on top of the other. That gives me a rectangular grid of data, and this is called a sinogram. Right? And the sinogram, as we'll see, essentially holds the same information as the original image, right? Which is not obvious at first, right? Each one of these functions is a function of L, right, is an integral through the whole object, right? You can see certain features in the sinogram. So as theta changes, say this dark feature here oscillates through the sinogram, and each one of these dark features are these circles here. And here's a bright feature, which is an ellipse, and you can see the ellipses also go through the object, and they change their width depending on what angle you're looking at them. If we're looking head on this way, they'll be thin. If we're looking down this way, they'll be a bit thicker. And then the most obvious thing is there is a boundary here, right, which is the boundary of the object itself. So if I have a projection that's from either the top down to the bottom, like if I'm looking down this way, my beam, my x-rays are coming down through here, the projection will be very wide, and that's one of these extrema here. When I put my sampling along here and I put parallel beams horizontally through the object, I have a narrower object on my projection data. So you can see as we move through different values of theta, we get this oscillating function. We can look at and say, let's look at this sinogram and ask the question, can we figure out, just looking at the sinogram, which angle we're projecting through the object? Right? Where is our detector? At what angle does the detector lie if I just look at this data here? So if this is L, right, from low values to high values, we'll say, and this is theta from, say, 0 through 2 pi down this way, what is this view? And can anybody take a guess? Okay, the first thing to look at is the width of this signal, of the main signal here, right? That's the first thing. So this looks like it's a minimum width. So that means the dimension of the large object is minimum on this projection view. So that means it's either going this way, right? And our detector's here, because this dimension is minimized on this ellipse that way. So it's either the x-rays are coming this way and hitting our detector over here, or they're coming this way and hitting our detector over here, right? And if we, say, so the question is like, which one of these, A, B, C, D, or E, is that function? Theta gets from 0 to 2 pi. L is just, the full length of the detector, we'll say, is this length here. So the other feature we can look at is this gobbledygook here, right? There's some stuff here. That's this, right? And so one assumes that if L is low here, high here, it's low here, high here, all of this stuff is on this side. It's this view that we're looking at. So the X-ray source is over here, we're putting parallel beams through the object, and our sampling is this one. And if I move this along, I will get, you know, different projections. So this sample down here is equivalent to sampling with L0 here and L max over here. Okay. Here is where the two dark features, as we're moving through theta, there will be a theta in which they are aligned and they're the same size. And so wherever they cross, that's going to be that angle, right? And so that's sort of how you can look at these sinograms and figure out what is what in there. And a good exercise is to ask yourself, okay, if I have a point in the scanner and it's at some position X, Y, and everything else is air and all I have is this point, what does the sinogram look like for that object? That's an exercise to do just in your head, right? And if I take that point and I move it twice as far away from the origin, what does the sinogram do? What does the sinogram look like? Now recall, this is the complete set of data that we can collect to try and reconstruct the picture. So this is our raw data, right? And from this raw data, we're going to try and reconstruct this picture. Right? You can kind of see that there's enough features in here, there's enough details and stuff that you should be able to reconstruct this picture. You know, really good radiologist could look at this and tell you what's going on. That's not true. So if I have a more complex object that has many interfering signals, right? So this object was pretty simple, and there were very detailed objects that didn't have a lot of interfering signals, so you could actually track their trajectory through the sinogram. When I have an object like this, and this is the one in the textbook, Prints and Links, this is what the sinogram looks like. And so it starts to look like this interferogram, which is very complicated, right? And it's hard to know what's actually going on with the data, the way we did with the way we tracked individual features, right? If we take one row of this, right, of this sinogram, and we back project it, this is the picture we get. So this is one G L theta function for a specific value of theta. You can see what that value is just by the angle of these lines. We're going to do just as we did with our 2x2 example, or 3x3. We're just going to back project the value all the way through the field of view. All right. And so that's what the image looks like when you do a single view back projected. Right. This is algebraically what that picture is, right? So it's B at a specific theta as a function of X, Y, right? Is G L theta, and this is L. This is the L that we have chosen. So this is the thing that changes, L along here. Theta is fixed, right? So that's, you know, the continuous function that expresses what that back projection is, right, in our two-dimensional space. In order to make it's called a laminogram, which is just naive back projection. We're just going to do this many times and add them all together, just like we did in our 3x3 example. You just take every one of these B thetas that you have and add them together. And that's what this integral is saying. Just for every theta, right, add up these B thetas to give an estimate of fxy. And we'll get this picture. And that's, remember, we saw it build up, that picture, as we added more of those basically B thetas together. So you can see you get a reasonably good picture, right, of the object. You know where all of the features are, where all the maxima are. However, each one of these dots is a very blurry version of the actual underlying disk, right, that was there. Again, this software that's in that I've put up on in MATLAB, I think it's 2020 in your folder, shows how to make sinograms or visualize sinograms for specific objects, right? And I've given you a set of examples in there, and that at the end of the class, we'll probably go through a few of those examples where you have like a specific set of individual pixel dots, and you can see what the sinogram looks like for those dots. Change these, make it a different object, make it a picture and stuff, and look at what the sinogram would look like. So this is a big deal. So that's back projection, sort of naive back projection. And now we're going to look at what's called the projection slice theorem. It's derived in the book. You can do the derivation if you want, but today we're just going to look at it as for what it means and try and understand it. Okay. So if we have an object, and our object is, I don't know why that didn't work, fxy, and so it's some kind of continuous function in the xy plane, right? And we've derived this function, which is the GL theta. So it's L is this axis, theta is this axis, and this is the G value that we have derived for that function. And let's suppose we know a priori the two-dimensional Fourier transform of this continuous function, right? We know a few examples, right? We know if this is a square, we know that over here we would have a two-dimensional sinc function, right? But for any continuous function that we know exists, we know there also exists its two-dimensional Fourier transform. And so this is the underlying truth that we're talking about here. These aren't the data or the images that we can make, but it's the underlying truth. When we take this function GL theta, if I got the, let's see if I'm let's start here. We take this function GL theta, and we take its Fourier transform along the L direction. Remember, theta is really a parameter now. We have a 1D function, which is like G of L. Along here, we take the Fourier transform of that. It turns out that that Fourier transform is a sample of the two-dimensional Fourier transform of the underlying object. Let's let this sink in a bit. We can do it the other way. If I know the two-dimensional Fourier transform of this function, and I go over here, and I have all of those values in the VU plane, which is spatial frequency plane, and I sample the values along here, right? And I take the inverse Fourier transform of those values along that angle, at an angle theta in the Fourier space, right? When I look at that one-dimensional inverse Fourier transform, it turns out to be GL theta. Yep.
So basically, there's this thing with you have a function, and you take a slice of it, and then you Fourier transform. It's a slice of the original function Fourier transform.
That's very close. That's very close, and that sounds almost more sensible than what is actually happening. It's not a slice of it you take of the function. You take the line integrals through the function along these lines. So we don't just slice through the fxy and then get a slice through the Fourier transform. That's not what's going on. What is going on is we integrate through the function to get the g value here, right? So these are line integrals through the function. And that gives us g. We take the Fourier transform of that thing, and that is a sampling through the Fourier transform of the full continuous function.
And then you also go back and say you do a line integral in Fourier, that, and then the inverse Fourier that gives you the line integral from the original.
Right. True. Well, no, the line integral from the Fourier would give you a sample through the object, a line sample through the object. So the line integral happens on this side, right? You take the Fourier transform of the line integral, you get a single sample through here, a line sample through here. It's not an integral through the Fourier transform, it's actually a line sample.
It's like a slice.
Yep. Yep. This is called the projection slice theorem. And so it's like a slice through Fourier space from these projections.
So it's slice in one.
Projections in the other. Yeah. And so this was, yeah, go ahead. Okay. L is the position along this line. So it's, you know, if we normalize position and we say this is 0 and this is 1, it's just its relative position along the line in millimeters. So it's spatial position. Here, oh yeah, this is the sample of the Fourier transform as a function of rho at the angle theta. Okay, so it's a sample of this guy. I guess this should actually be f at various values of rho. So that's a bit of a screw up in terms of terminology, but the reason it's capital G is because it is the Fourier transform of little g, right? So this function here that goes along this line, you have a 1D function. And we're going to call this capital G rho theta because, and it's a function of rho in the Fourier space, because it is the Fourier transform of little g, right? Now these projections have to happen. Then you take the Fourier transform and then you get this slice through the Fourier space. Yeah.
So is rho the Fourier analog for L?
It is, it's basically position in Fourier space in polar coordinates, right? Okay. So that's called a projection slice theorem. And it's absolutely essential really as a step towards creating convolution back projection, which will be the correct way to do back projection. We did naive back projection first, and we got these blurry pictures. We now look at the projection slice theorem, and this is going to give us a big hint on what we need to do in order to make a back projection algorithm that is correct, and it's going to be called convolution back projection. Okay. So in the terminology of our course, this is from the book, right? And then we'll map it to the terminology of our course, where instead of f, our object that we're trying to reconstruct is mu xy. Okay, it's the linear attenuation coefficient at a position in the patient, right? Xy. So it's mu. We can still call this g, right? Because it's the line integrals through mu xy gives us g. The Fourier transform of the underlying truth mu xy is capital U kx ky. And these are spatial frequencies, which are cycles per millimeter, right? Whereas these are spatial coordinates, millimeters, right? And then so our Fourier space will, and this will be true for MRI as well, will be kxy, I'm sorry, k sub y, K sub X. So this is cycles per millimeter in the X direction, cycles per millimeter in the Y direction, and then across at 45 degrees would be cycles per millimeter in the 45-degree plane wave direction, right? Okay. We can go into polar coordinates using K as our radial unit and theta, and transform, you know, our Fourier space into this form. And there we go. Okay. And so this formula down here, I should have a big red box around this, is the projection slice theorem in the notation of our course, right? In that the Fourier transform, this is just a Fourier transform using L as the independent variable, right? Of GL theta is this function, capital G K theta, which is a line sample through the Fourier transform of the object. Yeah.
So if Kx is spatial frequencies, like cycles per millimeter, then what is K by itself?
K is the magnitude of the cycles per millimeter, and theta tells you the direction of the plane wave, right? So if theta is down here, if theta is 0, then the plane wave is purely along the X direction. If theta is 90, then the plane wave is purely along the Y direction, and then you rotate, you know, with theta. Anyway. Okay. It's pretty fascinating, right? It's not, to me, it's not sort of viscerally or plainly obvious that this should be true, right? That the projection slice theorem should be true. So this is why it's, you know, helpful to be good at algebra, because you can just prove it using algebra. So, and in the book, they go through a proof, and you're welcome to do that. So some examples, some trivial examples are, if I have a square function or a rect function in the plane, right, then my basically spatial function is this. It's the two-dimensional rect function. We know the underlying Fourier transform of that is the product of two sinc functions, right? And so we know the true underlying function and the Fourier transform, and then we can just show that the projection at theta equals 0, right? So in this case, GL theta is just rect L, right? When we're projecting through 0, because we integrate across the square, we just get another rect function. And the Fourier transform of that is sinc K, which is just a sample through the two-dimensional sinc function we've got. Same thing at 90. It's in fact the identical thing, because when we're integrating horizontally, we're integrating through that square, and we get another rect function. Its Fourier transform is a sinc function, and it works out. It gets more complex if you do it at an angle, say 45 degrees. So I have the rect function, right, which is a square in the plane. And now we're going to ask, what is, you know, the integration? What is G, right, as at 45 degrees for the rect function? So when you think of that, you have a square, and you're integrating at 45-degree angles through the square, right? And so across the diagonal, you will have the maximum of that integral, and it will diminish as you go to the edges until you run out off the square. So it's going to be essentially a triangle. Is GL theta. Will look like this, right? And by this theorem, right, the Fourier transform of that function should give us whatever we see of the 2D sinc at 45 degrees, right? And so it does work out that is true. So you guys can work through this, and convince yourself that that is true with this example. That's just one example, but you're welcome to come up with other examples. So now that we have the projection slice theorem, we know how to map our raw data into Fourier space. So our raw data, remember, is we have a detector, it's got 1,000 elements. We take a shot, we get a picture that's GL theta, move it to another theta, get another one. So I have this sinogram. That's my raw data. We now know we can map that raw data into Fourier space, right? Because of this projection slice theorem. So here's one of those projections, GL theta. I take the 1D Fourier transform of it, and I get a sample through the Fourier transform of my image, right? So one way to think about reconstructing these images would be, why don't we just take these, lines or 1D samples through Fourier space and just stack them up like this. We'll stack them up radially, right? Just bump, 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 bump. They're samples through the Fourier transform. Then we can take that data, interpolate it onto a rectilinear grid. Since our points aren't on a rectilinear grid now, they're in this polar orientation. Just interpolate it onto a rectilinear grid, and then do a straight up discrete Fourier transform, 2D Fourier transform to get our picture. Right? So, that's Fourier reconstruction. You can't do that. It turns out that that is susceptible to artifacts, and so it's not done very often. But if everything was perfect in the system, that would work, right? So let's take a look at that, this polar version of the inverse Fourier transform, right? And so here we have our object, which is the thing we're trying to create through our inversion of our raw data. This is the Fourier transform of that object, the true Fourier transform of that object. This is the inverse, Fourier transform operator to get back to that object. Okay, so we've got the Fourier transform. This is how you write down the inverse Fourier transform. We're going to go back to space, and we're going to create mu xy. If we use our transformation to polar coordinates, with kx being k cos theta, ky being k sine theta, and then k itself being a positive number, which is off, from the origin, some distance, and write down that inverse Fourier transform in polar coordinates, right? It looks like this, right? So we swap out our variables for, kx and ky, and we get this transformation. Okay? The interesting thing about this is when you do that coordinate transformation and you write this equation in polar coordinates, you need to put in the Jacobian for this integration, right? And the Jacobian turns out to be k for this coordinate transformation, right? And everybody remember what a Jacobian is? When you go from, say, Cartesian coordinates to polar coordinates, you have to have a Jacobian to scale the elements over which you're doing your integration. When you move in d theta and dr, the amount of area that is covered is different than delta x, delta y. So that relative amount changes. And so when we do this polar inverse Fourier transform to get mu xy, this is what it looks like. And there's a big hint here as to what's going on. We'll see. So we've got now these are the data that we can actually make, right? From the GL theta, we have G, which is the Fourier transform of GL theta, K theta, and we're going to do the inverse Fourier transform of that. with the Jacobian in place. So this is going to get us to what is called filtered back projection, as opposed to just straight up naive back projection. Here's our original inverse Fourier transform to get from these data back to our image. And we'll gather terms up in the integral to basically use the definition of L in here for this, right? And we do the integration across dk, right, with this absolute value of k is the Jacobian. We're going to do that integration first in this 2D inverse Fourier transform. So this stuff in here is that inside stuff of this transform here, right? And we'll call that this function, which is this 1D Fourier transform here in terms of k, we'll call that G star L theta. So this is not GL theta, it's G star L theta. And the reason it's not GL theta, recall, is because we would get GL theta if we did the inverse Fourier transform of capital G K theta. Right? This is the Fourier transform of our GL theta. Right? What we're doing is this integration, which has this feature in it, which is different than what you would do just for an inverse Fourier transform. You now are weighting it by k, right, in that integration. So that's going to give us a different function, which is G asterisk L theta. When we look at this formula, all we're doing is adding up all of these functions as a function of theta. We're just taking each angle and just adding them together. Bum, 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 bum. So that's in effect doing the back projection, but we're not back projecting GL theta, we're back projecting this thing, G asterisk L theta, right? So when we look at G asterisk L theta, it's this function here, which is the inverse Fourier transform of this product, which is GK of theta, capital GK of theta times the absolute value of k. So this is where, remember, we looked at the convolution theorem, where a product in one domain is convolution in another domain, right? This is a product, right? Right? And we're taking the Fourier transform of a product. Therefore, in the spatial domain, this is equivalent to the Fourier transform of capital GK theta convolved with the Fourier transform of the absolute value of k, just by the convolution theorem. Right? That's why we spent some time learning the convolution theorem. So now these are our raw data that we have, that we've collected from our detector. Right? These are the things that we created this Fourier transform. Right? We can create this Fourier transform with samples through the Fourier space. And what we're going to do is convolve those data with the inverse Fourier transform of absolute value of k. Right? And so that we'll just call this thing some Q of L. When after we've taken the transform, it's in L, and we do that convolution. Is that clear? It's and so what that means is that if I have a projection, so this is my GL theta, and I look in the Fourier space at GK theta, so I take the Fourier transform, and now I have capital GK theta. I can multiply it by absolute value of k, which is just, it's called a ramp function, just goes up, right, linearly, like that. So I do that multiplication. I take the inverse Fourier transform of that product. That gives me G star L theta, and I back project those. Right? So this is the magical step. This is the step that's going to fix our issues of having blurry objects and everything. Equivalently, I can just remain in the space where I have my original raw data measurements, GL theta, and I can convolve them with the inverse Fourier transform of the ramp, right, which is this function. So remember the ramp, I can't seem to go backwards, unfortunately. The ramp just was a function that looked like that. This is its Fourier transform, the inverse Fourier transform of that function. Convolve these two. So then I get, again, G asterisk L theta, which is the convolution, right, of these two. And I back project those to get my picture. So let's see how that changes things. Remember, when we had the example where we had a disk and we had it at different angles and then we back projected and we got a blurry version of a disk for our image with simple back projection. Oops. Okay. So here's our data that we've measured, which is GL theta, right? That's what's on our detector. Now we're going to convolve that data with the inverse Fourier transform of the ramp and get G asterisk L theta. And it looks like this. Looks a lot different, right, than this. So we were back projecting these. We're now going to back project these, right, to create our estimate of mu xy. A couple of features look promising. One is I have a flat top, right, which is good because my object is a disk, right? So I do want a flat top in my picture of a disk. Also, I have these negative lobes away from the peak that will likely subtract away a lot of that blur signal that was spreading out from my object. So this is what one of those looks like when it's back projected. This is what 4, 64, 512. And so you get the object without that haze, without that blur. So remember above we had this array of circles, array of disks, and this was what the sinogram looked like, which was GL theta with the thetas stacked one on top of the other to create that sinogram. Here's that sinogram, and this is what the stack of G asterisk L theta looks like. It looks something like this, right? And if we look at a sample, in our original one, it looked like this. Remember, GL theta is always positive, right? So it was these positive values along here. After we convolve this function with the inverse Fourier transform of a ramp, we get this. And now we have negative and positive values over here, right? And the background is 0. So we're going to back project these things now. And so when we look at what that back projection looks like, it's centered around 0 at this point, right? And it looks quite different than the original one. And here's what it looks like with 40 out of 240 views, 80 out of 240, 120, and then 240. Okay, so that's projecting from here to here using just these views in our filtered sinogram. We get this picture. Projecting more views, we get this picture. More views, we get this, and then finally that. And now we have a picture that doesn't have all that haze in the background. And all of that came from the realization that the data that we have are radial lines through Fourier space, right? So when you just back project that data, you basically overweight the DC components. You're oversampled at the center of the Fourier space, and that gets compensated for by this ramp filter, right? So here's the fundamental ramp filter itself that just is is just the magnitude of K as we move away in spatial frequency. And when we look at its inverse Fourier transform, it looks something like this, right? So it's got a peak and then a lot of negative side lobes like this. So in essence, what we're doing is we're filtering our data, right? Where we've got some data in GL theta. We look at it in Fourier space, and then we multiply it by this thing, which is a filter, right? This is not a low pass filter, right? A traditional filter, you say, oh, I'm going to get rid of all my high frequency noise, has a big thing at 0, and then it rolls off at higher frequencies. And that's a smoothing filter. This is anything but a smoothing filter. It is not a smoothing filter, right? It amplifies values at higher and higher frequencies, right? And so the high frequency values get amplified more than the lower frequency values. And the reason this weighting, just from a sort of common sense Gestalt reasoning, is that as we go out in higher and higher frequencies, as K gets larger, the density of samples I have out there gets lower and lower, right? And it actually gets lower as 1 over K, right? So if I'm on a line through Fourier space, on a radial line, and I look at my neighboring points as we're all traveling out together, it gets to be lower and lower density. And so this correction factor basically multiplies the weighting to compensate for that density, right? Yeah?
I guess it does kind of make intuitive sense because we're kind of sharpening the image, which is reducing both frequencies and increasing.
Absolutely.
So the center, which is the low frequencies, is 0, and then the edges are boosted.
Boosted a lot, yeah. And you can see that when we looked at the, if we go back to this, right? Where, so what did convolution do? Well, it really boosted making this edge, right? So as these negative lobes sort of scooch along edges, it's going to subtract away all the stuff that was blurred out, right? And so that it's an interesting thing. We'll look at artifacts later, and if you have a little blip, some problem on your data, like some noise blip, when you do the convolution, that becomes a very large thing. And so it back projects a lot of noise into your image. So it's something we have to take into account. But the interesting thing also is that, you know, this as a filter, right? If we now just think of it as a filter that we're putting on our raw data, boosting high frequencies like this is not often done because it produces a lot of weird artifacts in terms of ringing off edges, in terms of amplification of noise at high frequencies, etc. And so over time, even though this is analytically what you need to do to your data to recover your object exactly, in a noise situation and in a situation where you're slightly undersampled or something, this will produce issues, right? And so having a filter that abruptly changes from its maximum value to 0 at the highest frequency is not usually a good idea in any kind of signaling. If you have absolutely noiseless data and you are sampled absolutely adequately, things will work out. However, to make the pictures look a little bit smoother, more appealing, oftentimes these high frequencies aren't amplified as much. You sacrifice some resolution, and you just tamp down the high frequencies. And the convolution kernel broadens, it's not as sharp, and these negative lobes are a little bit less, but you get a smoother, milkier looking image, right? And then this can keep going. You can crank it down more. This is called a Shep-Logan filter. This was a cottage industry for a while. What's the best filter? And then here's the cosine 2 filter where it actually goes to 0 at the highest frequency. So you just go down and that looks like this as a convolution. And then here's one, which is a Hanning filter, which is ultimately smoothing in that it not only goes to 0, but its derivative goes to 0. So it curves down, and so you downweight a lot of this high frequency stuff in order to make a smoother, quote unquote, better looking picture. Okay? So you'll take some of that blurring back in order to get to reduce noise. Okay? And so all of these filters are available on a scanner. They usually have different buttons. And if you press the bone filter, right, it usually is this, which is just the ramp filter. And you will get very high resolution pictures with high frequency components in them, but the noise will be pretty high. So just the random noise in the picture. So we can see here with this filter, if I had a rectangular object, I would get this picture. And then when I use the Hanning, which is a smoothing filter here, I use that down here, the edges get softened up. Right? Here's an example that I got last Thursday on our scanner. We were measuring the point spread function by putting a little bead. This is just a ballpoint pen, 0.25 millimeter bead in the scanner, and it gives a bright signal here. And this is with the bone filter reconstruction, and this is with the standard filter. So they don't tell you what it is, they just give it some name, right? Bone filter is likely very much like the ramp filter if it isn't exactly the ramp filter. And you can see the object itself, this little bead, which is much smaller actually than a pixel, is smaller in this picture than it is in this one. So it's a tighter, higher resolution picture. That the representation of that bead is smaller in space, using the bone filter rather than the standard filter. However, look at all these artifacts you get ringing off these edges because of that. Remember, the convolution kernel had all of those cycle rings, and so when you get a very abrupt change, you get high frequency ringing off edges. You get a very high background noise value because it's emitting a lot of high frequency noise that for this object, you don't need high frequency to estimate the value of this thing. And so this is what the standard filter makes that look like. Radiologists often like this. Excuse me. Excuse me. Should have brought something to drink. Okay. And then if you look down, this is air. If you look down at the baseline, you still see these ringing things down at the bottom of the scan. Higher noise in the air, less noise and less ringing over here. Then the discrete kernels that are used. So this is the ramp filter. So when this is the true value, right? Usually when the convolution is done, it's done as a discrete version of that. And so these are pictures of those convolution filters. And what happens, say, to a rectangle G of L when you convolve it with the ramp filter? It looks like this. You get these ears, right? Batman ears. And then as we go to filters that roll off higher frequencies, this is what the convolution starts looking like, and then the object itself goes down. You can't totally get rid of these negative lobes, right? Otherwise, you're just back to where you started, which was that blurrier picture. Okay, so that's 12:14. What we can do now quickly is take a look at the MATLAB function. Do I have MATLAB going? Oh, I do. So are there any other questions you want to ask about the? So there, just to recap before we do this, the things we talked about today are the core things in CT, right? The things that really you want to know, which is the radon transform, right? The projection slice theorem and convolution back projection. Those are the three things that if you write something down and you want to know what what it is about CT, those are the three things you want to know. So I think so that's which one is this? Okay, good. So this piece of code is, can I not move it? Ah, here we go. Is designed so that you can play around with different structures and different sampling schemes to create your own sinogram, right? And then do the inverse radon transform on that sinogram to look at a picture. And so a couple of example images are provided by me here. You can make your own picture. You can see how. So what you do with this program is you just select one of these images that you want to look at. This is the Shep Logan Phantom was selected to 1. We make that 0. We can look at a set of small squares. We'll set that to 1. Just run the whole thing again. It clears everything out and just pops up the pictures again, right? And so this is a very simple picture. It's got 2 squares very close to each other and 2 squares very close to each other at different places in the field of view. When you take the radon transform, you get the sinogram that would be observed from these pictures, right? So this is L along this direction, and this is theta this, right? So you can put whatever you want in here, and then you'll get what GL theta would look like. It should be labeled, yeah, it says GL theta here, right? From that data, you can just do the inverse radon transform and get back to your original picture. Or you can modify this data and say, this is the raw data that we would take, right? Suppose we couldn't take it all. Suppose we could only take this much of it for whatever reason, right? We're going to cut down. What does that do to my picture? What artifacts do I generate? And this is the estimate of those 2 squares given a partial data acquisition. We could try other things like, you know, what happens if I do 64 views instead of 640 views? Right? Things like that. If I could get away with sampling over a narrower range of theta, that means I can reduce my acquisition time by, say, a factor of 2, right? And make a picture. Is that picture good enough to do what I want to do? So that's, so those are the central squares. So you can just click on the, so this is a really slick user interface. You just set things to 1 and run it again. So this one is actually a clinical case. I hope it works. Yeah. So here's an actual image, right? And this is the sinogram from that image. And there's the inverse, and there's partial data sampling. This is the Fourier space of the image and something. So when you go into the code, you can just look at it and change it as you wish. That's about all there is to say about this. So you're welcome to, you know, modify the code, and you can, here's the first projection angle is 0, the last is 180. Delta theta is 0.5. Let's make delta theta 5, see if that works. Right. Okay, so now instead of every ½ degree, I take a projection. I take a projection every 5 degrees and put that data through the inverse radon transform and say, what does my picture look like? And this is what it looks like, right? And so you can start to get a feel for, you know, a visceral feel for how you need to sample something like this to get the picture you want. For certain things, for certain tasks, like what is the area of the aorta? This picture's perfectly fine, right? So you probably don't need to use as much radiation, and you can use fewer views, etc. Right? So you can play around with it. Okay. And if you have any questions, just shoot me an email. Give us a snippet of code and say, like, what on earth am I supposed to do with that?